Okay, let's start here. We're going to try to stay close to the machine so that people can hear me. For those people who are watching the tape. Um, so so you can see there, I posted the sample test for test number 3. So there's the announcement. So it's on Blackboard. Of course, it's just the blank sample test so far, and then so the answers will be sometime, not this week, but next week, right um, after Thanksgiving. Um, we have this homework that's due tonight, right? This was on areas of the plane, right? So double integration, but to compute areas in the plane. The more exotic application of double integrals for computing volume, that's not due until next Monday. That's this homework, and we still have some examples to go through with setting up these double integrals for volume. And well, we'll see how far we make it today, because we have we have quite a bit of algebra to work through today in some of these examples. And then, but we'll see if we get to how you can change your coordinate system from rectangular coordinates, Cartesian coordinates, just regular x, y coordinates, to polar coordinates. And sometimes that simplifies this integration. Okay, not always, but sometimes it simplifies it. Or if you're integrating over a region that is more easily described with polar coordinates rather than with rectangular coordinates. Um, uh, uh, Computing your double integrals in polar coordinates rather than in rectangular coordinates will make the integration process easier. Um, so we're trying to get to that, but we'll see how far we get here today in the examples. So I want to go ahead and start because we were setting up some examples, last week, but not this one. We were setting up some examples last week, but we just set up the double integrals, but we never evaluated the double integrals. So I want to do a little bit more evaluation of double integrals today by hand. But and of course, evaluating integrals always by hand can be challenging, right? Sometimes, and then of course, double integrals just makes it doubly so. So I do want to encourage you to remember, and we'll see examples of it again today. To if you get stuck, right, okay, on evaluating a double integral, go ahead and use some tool, a symbolic a manipulator like Wolfram Alpha. There's a link to that on the homework at the top, right? But you can use, if you have some other tool that you're aware of, or if your graphic calculator does integration well, then don't hesitate to use that, though. Okay, right? But I don't want us to be lazy either. So we're going to go through some examples today of trying to evaluate these double integrals by hand, just to show you that you can in many cases you can attack it. You do have the skills if you can recall them from calculus 2 to make a solid start, at least on evaluating some of these double integrals. So last time we had set up this double integral to compute this area, this volume. So we were looking for the volume beneath this surface. That surface's formula is what ends up being in the integral here. So it was z equals 1 minus 1/2 x squared minus 1/2 y squared, right? That's that surface above the xy plane. And then our region of integration here was very simple. It was just 0 to 1 on the x-axis and 0 to 1 on the y-axis. So you just had this nice square region of integration, right? So you're just trying to find this volume, right, beneath that surface down to the xy plane, right, but just over this square. So it looks like when we were setting this up last time, we were thinking of slicing it right, with a plane that was parallel to the YZ plane. In other words, we fixed a value for X, right? We fixed the value for X on the X axis, and then we cut through that volume vertically, right, with a plane here that was parallel to this to the backside of this volume, right, the YZ plane. And then remember, we computed the area of that, and then we integrated along the x-axis, right, to find the total volume. So here's sort of a picture of that. This is kind of a picture in some sense, right, of that double integral, right? Remember, the inside part is computing the area of this vertical slice, right? Okay, and then you integrate a bunch of those vertical slices, right, from front to back along the x-axis, from 0 to 1 along the x-axis, and that would give you then a volume, right? Okay, when you integrate a bunch of areas, right, infinitely many areas, right, you'll get a volume. So there's the double integral that we created. But we didn't evaluate that, so we really don't know yet what that volume is. So I want to go ahead and just as a little bit of practice here, let's try. Let's see if we can actually evaluate that double integral. All right. So this is just an exercise in algebra and calculus, and I guess ultimately arithmetic. Actually, the arithmetic might be the worst part of this. Maybe not, because the limits of integration here are very simple, right? We had this nice rectangular region of integration. So our limits of integration in our double integral just turned out to be the boundaries of this region, right? So it's 0 to 1 on the x-axis, but then also 0 to 1 along the y-axis. So this is one case where it wasn't difficult to set up the limits of integration, but sometimes the limits of integration are messy to set up if your region of integration is kind of more irregular, right? But here, very simple. So you're going to really like rectangular regions of integration. This is what I was mentioning earlier. Sometimes if these regions of integration get a really strange shape, sometimes they're easier to describe in polar coordinates. So especially if they involve like disks, they're easier to describe in polar coordinates, and then it's easier to evaluate the double integral in polar coordinates. That's why I was saying we're trying to get to that point. It's really not difficult to make the switch to polar coordinates. That sounds a little bit scary because you're thinking, oh my God, polar coordinates again. But that's not so bad. Yeah. Well, no, yeah, no, not the washer method, but our regions of integration may look like washers. Okay, right? They may look like a disc, right? A circle with a middle cut out. That's usually what you would call a washer. Actually, that has the technical name for that is an annulus. And but it might just be a disc. It might just be a solid disc without middle of it cut out. Okay. And those sorts of things are easy to describe in polar coordinates. You can describe them in rectangular coordinates also, but they're a little bit the inequalities that describe the disk are easy to write in polar coordinates. So sometimes it's convenient, if that is your region of integration, to switch your coordinate system to polar coordinates. Okay, but here we're just dealing with just plain old vanilla rectangular coordinates here, right? So let's try to integrate here. So our inner variable of integration here, right, is y. So we're going to treat x as a constant. So that makes this easy to that makes this expression easy to integrate, right? You're just going to get let's see, I think a y here, right? And then there you're just going to attach a y, right? Because the 1/2 x squared is just a constant. So you just get to attach a y there also, just like you attached a y to the 1, right? And then now here, though, you have to use the any power rule, right? So so you will have to do a little bit of work there, right? So add 1 to the exponent and then divide by the new exponent. Don't forget that's going to be multiplied by 1/2, though, right? So ultimately there it looks like you're going to get a sixth, right? And then but the limits of integration, right, are really nice, right? So they're just from 0 to 1. So you're going to plug the 1 in, of course, right? You're going to plug the 0 in and then take the difference. But it's very easy when you plug the 0 in, right? Because all these terms involve a factor of y. So when you plug 0 in for y, all those terms are just going to disappear. So you don't get anything, right? So really all you're worried about is what happens when you plug in a 1. And that should be pretty easy to evaluate too, right? So when you plug in a 1, let's see, what do we get there? What, 1 and then minus 1/2 x squared, is that right? And then what's all of this going to be? That's a little bit messier. Is that 1/6? Yeah, so minus 1/6 here, right? And then don't forget your dx. I guess you can combine the 1 and the 1/6. If we want to rewrite all of this, right, we can combine the 1 and the 1/6. Let's not rewrite it. Let's just do it right here. So 1 minus 1/6 is 5/6, right? So it looks like we're going to get 5/6 right there minus the 1/2 x squared. And now we just integrate that, right, with respect to x. So that's so easy. That's just going to be 5/6x, right? Minus, and then here we have that darn x cubed again, right? So when we integrate that, we get x cubed over 3, right? And then this is just evaluated from 0 to 1. And again, so easy to evaluate it at 0, right? Because you have a factor of x in both terms. So when you plug 0 in for x, right, you're just going to get 0. So really all that happens, really the result is what happens when you plug the 1 in, right? And so that looks like what, 5/6 minus, is that 1/6 again? So that's 4/6, which I think is better known as 2/3, right? So it looks like it's like our volume there is just 2/3. Okay. All right. So not bad at all, right? So on a test, you might be hoping for, something as straightforward as this, right? Okay, to as a double integral that you might want to evaluate, because this just just have to use the power rule, and the arithmetic turns out to be very simple. So it's easy there to compute by hand. This is about as straightforward as they'll get. Okay, all right, in terms of effort there. So they can be worse, all right? And that's where, again, sometimes we have to rely on Wolfram Alpha to help us here, right? So we set up this one also. I don't know if we evaluated this one. Okay, so we wanted again to find the volume beneath this surface. Okay, right? And the formula for that surface was z equal e to the minus x squared. So it's not a complicated formula for the surface, except it involves that power of e, right? And well, the surface, at least this part of the surface, is not very interesting. I wish we could see more of the surface. I should have plotted more of the surface to see if that surface ever gets more unusual than that. Okay, but probably not, because it doesn't involve the variable y, right? So so probably not going to be that interesting a surface anyway. What was a little bit different here, though, right, is the region of integration was a little bit more complicated, because we were only going to use this triangle as the region of integration. So we weren't using this whole rectangle, right, from 0 to 1 on the x-axis and from 0 to 1 on the y-axis, like we did in the previous problem. We were only using half of that rectangle, this triangle. So that was bounded by y equals 0. That's the x-axis, right? Okay, and x equals 1, this straight line, right? Okay, and then y equals x, which cuts this square, right? Just directly in two. So it looks like what we did to create the double integral is like in the previous problem, right? We fixed a value for x, right? Okay, and so we thought of that as, you know, cutting through this volume with a vertical plane, right? That's going to be parallel to the YZ plane, right? So we fixed x, so that means that y is going to be our first variable, our inner variable of integration, right? And notice x is running from I'm sorry, when you fix x, right? Notice that the y values, right? The y values here, if we move along the y-axis where we fix the x, right? The y values are starting at 0, right? But then they're only moving up to this line, and that's the line y equals x. So the y values are only going as far as the x value itself, right? And then just use your formula for your surface, right, as your integrand. And then, so the inner integral, right? Remember, that gives you an area of a two-dimensional region, right? The cross section when you cut that vertical plane, right, through your volume. And then you integrate those areas together, right? Okay, those infinitesimally small areas, right? You integrate those together to get an actual volume. And so that would be from 0 to 1 on the x-axis, right? So your second variable integration is x. So we end up with this expression. We end up with this expression for volume. And then it's just a matter of evaluating that, which is not going to be an easy chore because it is not easy to evaluate, find the antiderivative of e to the minus x squared. Okay, if that were e to the minus x, it'd be easy to find the antiderivative, but not easy to find the e to the minus x squared. Okay, so that presents a real challenge to us. So I think on this one, it really would behoove you here to use Wolfram alpha. Okay, all right, because of the challenge of trying to integrate e to the minus x squared. All right, e to the minus x, you can integrate that with just simple substitution. Okay, but e to the minus x squared, much worse. So so let's try that. So do y'all have that written down somewhere? I'm going to just switch to Wolfram alpha and see if I can. I'm going to switch to Wolfram alpha and see if I can type in that. See if I can type in that that double integral. See if I can find Wolfram alpha to start with. So there's our first challenge. Okay, so there it is. And so it worked. You can use just natural language here and sort of natural language here in Wolfram alpha to do integration. Just use integrate, okay? But you're doing a double integral, so you have to integrate inside of an integration, right? So use parentheses for grouping here, and then you want to integrate again. And what are we integrating now? So what was that? What was that? What was that expression? It involved an e, I think, right? Was it e to the minus x squared? So e to the minus x squared, you know, of course, you can get, I think Wolfram will recognize e there, hopefully. All right. So if it doesn't, we'll go back and fix that. I know another way of entering e to a power. So there's e to the minus x squared. What were our limits of integration there? Right. Remember, this is y, right? Though, so y is running from 0 to x, correct? So there's the inner integral. And for the outer integral, what were its limits of integration? From what, x equals 0 to x equals 1? No, no. No, it's x equals 0 to 1. Z is not going to show up in anywhere in the double integral. Oh. Yeah, because the formula for your surface is z equals. So actually, z is here. Elijah, Z is here, but it's kind of invisible because this formula is Z equals e to the minus x squared, right? So that formula gives you the height of that surface, right? Okay, which is the Z coordinate. This, by the way, now I think all of these examples, we have a surface above the xy plane. So the surface is going to be of the form z equal to some form, z equals to some formula involving x and y, right? Okay. This formula only involved x, but it could have a y in it as well. Let's see if we got that entered right and if it will do a calculation for us. So I'm hopeful. Oh, and so there it is, right? Um, and Wolfram is very smart, so it's going to give us the exact value, which is e minus 1 over 2e, all right? But that happens to be 0.31606, so that volume is close to the volume of the picture before, right? Okay, that picture before was 2/3 as the volume, and this one is about 1/3, right? As the volume. Now, if we see if I can switch back here without closing something. If we had switched the order of integration, so if I wanted to do x first and y second, what would this have looked like? So in other words, if I thought of slicing the volume with a plane that is parallel to a vertical plane that was parallel to the xz plane. In other words, if I fix the value for y first, right? Okay. If I fix the value for y first, okay, and so slice through this with this plane that is parallel to the right, I'm sorry, the left side of this volume, right, which is the xz plane. So fix a value for y and then let x vary, right? Okay. Compute the area of this little thin slice beneath the surface and then integrate all of those areas together from left to right instead of from front to back. Well, what is the outer integral going to look like? It's still going to be from 0 to 1, right? Exactly right. Still going to be from 0 to 1. But here you're going from 0 to 1, Elijah, along what? Yeah, along the x-axis, right? See, so you're see, we're fixing y first, so your inner variable of integration is going to be x, right? It's the x that's varying, right? And then in the outer integration, your y will be varying, but also they're 0 to 1, right? Okay. It's sort of bad to point out it on the y-axis, right? Because you're really going from 0 to 1 here, correct? But still from 0 to 1 along the y-axis, right? Now, but what about the formula is still e to the minus x squared because the height of that surface is still e to the minus x squared. So that stays the same. What's tricky here are what are the inner limits of integration? So where notice it's x that's notice it's x that's varying here, right? How is x varying? Well, I can figure out where x is ending up at. Where's x going to end up at? 1, right? Yeah, right there. X is 1, right? So we got that. But where does x start at? So it starts at this line, right? Yeah, it starts at y. Perfect. Yeah, David, excellent, right? It starts at y, correct? Right. Um, Starts at this line, which is x equal y, right? So don't write x there though, right? Because x is the variable of integration. So write y, right? So these two things should turn out the these two integrals should give you the same value, right? Actually, in the notes, if you look at the notes there, there is the Wolfram Alpha command, right, for the double integral, but in the order dx dy instead of dy dx. All right, and notice we get the same. Of course, you get the same result, right? Because the volume is the same either way. So the result there is still e minus 1 over 2e. So if you want to look in the notes, right, that shows you how you can type in to Wolfram Alpha, a command to do double integration, or actually triple integration there as well. All right, if you like. Here, I was just going to draw the region of integration. Sometimes that's helpful on the xy plane to draw the region of integration. It really doesn't help us much here because we can see pretty good the region of integration in this picture. There's the region of integration, right? But notice it's enclosed in that that square, right? 0 to 1 on the x-axis, 0 to 1 in the y-axis, but it's only half of that. Which half of that is that? If you draw that separately, I think it's this is what the region of integration looks like in the xy plane. Okay. Okay, well, let's attack one more. Now, this is phrased separately, but we're going to be able to answer this easily with a double integral. So this says find the average value of this function over this rectangle. Of course, that's a function of two variables, 1/2 xy. It might be easy to write it as z equals 1/2 xy, right? So, of course, when you plot z equals 1/2 x, right, you're going to get a surface. You're going to get some sort of surface. And we're interested in the surface just above this region of integration. So we have a very nice region of integration here. It's just a rectangle. So this is our favorite type of region of integration because this makes it easy to write down the upper and lower bounds for your integrals. All right. Okay. So and when it's easy to write down your upper and lower bounds for the integrals, then it doesn't matter really which order you integration either. Okay. But what's asked for here is not the volume beneath beneath that surface down to this rectangle. But what you're asked for is what's the average height of that surface, right? That surface is some height above the XY plane. So we want to know is on average, how high is that surface above the XY plane over this region? So what's the average Z value, in other words, over this entire region? Right? Okay. So at first that sounds like a complicated question, but it's very easy to answer. All you have to do is find the volume of the surface and divide by the area of the region. That will give you the average height of the surface, okay, above the region. So just compute the volume, right? And then divide by the area of the region. So you're really just back to a volume problem. This is really the volume. Well, unless finding the area of the region is difficult, okay, but which it could be, right, if you have a really crazy region. But this region is very simple. What's the area of this region? Of course, what? Just 12, right? Because this region is a rectangle, so you just take the length times the width, right? Okay, and there you get the area of that region. So not difficult to find the area. But now what about the volume? Okay, so that may require some work, right? Because that's going to involve a double integral, right? So let's see if we can set up that double integral, but it should be really easy. What order of integration do y'all want? Do you want dx dy or dy dx? Sometimes it can really make a difference, but I think here it's kind of not going to make a difference at all. right? So what do y'all like? You want dy dx? So if we do dy dx, right, what does that mean? That means we're first fixing a value for x, right? Ooh, I almost drew that wrong. So at first we're fixing a value for x, correct? And we're letting y vary first. So you fix a value for x and then you're going to let y vary there, right? Above that or below, as it were, that a fixed value for x. So what's y varying from and to? Where's y starting at here? 0, right? And going up to what? 3. Sure, right. Okay. And so in other words, you're computing this cross section, right, of this volume above this vertical line, the cross section directly above this vertical line, and then you're integrating all those cross section areas together, right, from left to right. So in the second integral, x is varying from what, 0 to 4? Well, you can hardly miss, right? You can hardly miss those boundaries of integration because your region of integration is only 0 to 3 on the x-axis, right, and 0 to 4 on the y-axis. So those are pretty automatic. And let's see, what are we integrating? What's the value for z? What's the height here? Yeah, 1/2 xy. All right. So if we can get through that integral, then we're in pretty good shape. This one we should be able to do, right? By hand? I hope so. But if not, if we get stuck, again, we can use Wolfram Alpha, right, to help us with this. All right, so let's see. How do you integrate this? 1/2 xy with respect to y. You're just going to use the power rule, right? So you're going to get 1/2 x and then times y squared over 2, right? Don't have to do anything with the 1/2 x, right? Because it's just a constant. But the y, you just need to apply the power rule to that. So let's see, we have a 1/2 times a 1/2. Oops, I forgot. I need to evaluate this from what? 0 to 3. Well, I was going to factor out the 1/4, but I'm not sure that's even really necessary, right? When you plug 0 in for y, of course, that's going to just give you 0. So all you have to do is really plug the 3 in, right, for the y. So what does that end up being there? You plug 3 in, that's 9/2 times the 1/2, right? So you get 9/4. X, is that it? Is it that easy? Did I make an arithmetic mistake? Yeah, plug 3 in for y. That's 3 squared is 9, 9/2, and then you have the extra 1/2 there. That's going to be 9/4, and then the x is just tagging along, right? At this point. And now we do something with the x, right? Because now we're integrating with respect to x, so we have to use the power rule again. So we get x squared over 2, right? Oops, I don't need my integral sign anymore because I've already done that. And now I'm evaluating from 0 to 4. Well, again, when you substitute 0 for x, that's just going to be 0. So all we have to do is worry about substituting the 4. So what is that? What now? Oh, it's all just 18? Really? 9/4 times 8? Oh, yeah, you're right. That's 18. Okay. So the volume is 18. So what we were looking for, remember, was the average height of this surface. Oh, by the way, here's the surface. I did have a graph of the surface. I should have showed you there. a little while ago, right? Okay, so there's the surface. Looks like what's that place in the park? The amphitheater there in the yeah. Somehow it looks like the the stage at Miller Theater. All right. Well, anyway, all of the imagery aside, what is the average height of that surface? So see, now it's easy to compute, right? Because you just have to take the volume, which is 18, and divide it by 12. So we get what, 3/2? Oh, that looks like reasonable, right? Here's 3/2. So we're thinking on average that surface is at 3/2. Okay. Oh, so we can do some of these double integrals by hand, and they're not that painful. But you know, depending on the formula for your surface, right, they can get painful. Okay. So let's look at a couple of more complicated examples and see how far we can get into the integrating these things by hand. All right. So now these are going to be not a little bit tougher, actually a lot tougher. All right. So get prepared. Actually, they're tougher examples right from the start. So, but the picture is easy. Okay. So we want to find the volume between this surface. So that's some sort of quadratic surface, right? So y'all could look that up in your catalog and tell me what sort of surface that is. But so anyway, so you got that shape, right? Down to the xy plane, right? So just the volume that you see here. Okay. And so just setting up the double integral to represent the volume already it does take a little bit of work. Okay. So what I want to do here is so what I'm going to try to do is fix the value for y. Can y'all see that in the picture? So I'm going to fix a value for y somewhere here, there on the y-axis. Actually, let me draw there's my fixed value for y, right? Okay. And then I'm going to take a slice here, you know, as usual, right? Take that vertical slice through the volume. And, you know, that vertical slice is, in this case, going to be parallel to the XZ plane, right? Going to be parallel to the XZ plane because we're fixing the value for y. So what's my see if I can even find room to write down this this double integral. Oh, I have some room down here. So just to get started here, so we're gonna have a double integral. We know that. But what about the way I've described you know, computing the volume? What is my order of integration here? So say I'm taking this slice, right, which is parallel to the XZ plane. So I got that slice by fixing a value for y, right? Okay, along the y-axis. So the y is fixed, right, to compute this area of this slice. So what's varying then if the y is fixed? Yeah, x is what is going to change at first, right? Okay, because you've got to compute right, x is changing, right, if the y is fixed, to compute just the area, the two-dimensional area of this cross section that I've drawn here. But I could have drawn, you know, I could have drawn the cross section the other way, right? I could have drawn a cross section like this, right? There I would be fixing a value for x, right? Instead of fixing a value for y. So, but we never answered my question. If I do it like this, then it's d what, x first, right? And then dy? Okay. All right, now, now now we got to find the limits of integration. I think I know what the y's are, though. All right, because, well, no, I don't even know what the y's are yet. Okay. Um, uh, um, but you can sort of see in the picture, right? Where the y is going to stop and start, correct? Because you're going to compute a cross section like this all the way from left to right, right? Okay, so you're going to start with a cross section way over here, compute the area of that cross section, and continue computing areas of those cross sections and integrate all those areas together up to this point on the y-axis, right? So we got to figure out what are those two values on the y-axis. Maybe that's not completely clear. So here's where it really is going to help us to draw a picture in the XY plane of the region of integration. So the region of integration is right here where my my volume, right, that intersects with the XY plane. So it looks kind of like a circle, but I don't think it's a circle, but it is circular, right? Where that volume intersects with the XY plane. How do we find that, though? We need to find that exactly. So how do we do that? Yeah, what do we set to 0 here? Z is going to be 0, right? In the XY plane, Z is 0, correct? Right? So set Z to 0, and let's look at this equation and see if we can figure out what that thing looks like. Okay. Well, I really don't need to figure out what it looks like. So I know it's kind of some sort of oval shape, right? But let's see if we can plot it in the let's see if we can plot it in the XY plane. So let's see, let's rewrite this a little bit. This would look better if it were what, x plus 2y squared, that equals 4, right? Okay. And y'all have any idea what that thing is? It's not a circle. If it were x squared plus y squared equal 4, that would be a circle. So if you didn't have this coefficient, that would be a circle, and it would be centered at the origin, and the radius would be 2. So you would have a nice circle. Unfortunately, the 2 messes things up. Okay, so you don't quite have a circle. Well, what's the next best thing to a circle? Yeah, we have an ellipse, right? In the XY plane, we have an ellipse, okay? So this is going to be an ellipse. Actually, we could plot it's going to be an ellipse centered at the origin. So if we can just find the intercepts, we could, if we just find the intercepts, we can plot this. So if we can find the XY intercepts, it's all right. Let's see. So this is x squared, by the way, so can't drop that. So what are the intercepts there? What's the x-intercept? If you plug 0 in for y, what are you going to get for x? What? 2 and minus 2, right? Okay. So 2 and minus 2. Let me put 2 way over here. And minus 2 back there. So there's 2 and there's minus 2. Okay. And what about for the y-intercepts? Well, let's see. If we plug 0 in for x, what happens here? Get what? Y squared is equal to 2, which means that y is what? Plus or minus square root of 2? Oh, okay. All right. So not bad. So the y-intercept plus or minus square root of 2. The positive square root of 2 is about right there. It's close to 1.5, but not quite, right? And minus square root of 2 is about right there. So this is positive square root of 2, and this is minus square root of 2. So you get just a slightly, it's just a very slightly elongated ellipse there. It's very close to a circle, but not quite. So I drew it really poorly on one side. Let me try this one. And I can make that a little bit better. Okay, well, that's a little bit better. Now I forgot what did so there's the trace in the XY plane, but I so that tells us something already about our limits of integration. What is the limits of integration on Y going to be? See, remember we're going to take this cross section, right? Compute the area of this cross section. We do that by fixing a value for Y at first, right? But ultimately we have to find cross sections for all values of Y from the left to the right. So where would our Y start at? Well, just look in this picture, right? Minus the square root of 2, right? Okay. So this is minus the square root of 2 up to square root of 2, right? Okay. So I got that figured out. Now let's see. Let's put this line in here because that's going to give us, that line is going to help us understand the that line is going to help us understand these inner limits of integration, right? So where have I just sort of roughly drawn that line? That's on the positive side of the y-axis, right? So it's just maybe right there, something like that. I don't know exactly, right? Okay, we fixed a value for y, correct? Somewhere there on the positive side of the y-axis, right? So we can see that in our inner limits of integration, right, x is running from this side of the ellipse to this side of the ellipse. Oh boy, okay? So I've got to be able to write this side of the ellipse, and I've got to be able to write this side of the ellipse as a function of y, okay? Right? As a function of y. So take your ellipse and just solve it for x. That's the moral of the story here. All right. So take the ellipse, and there's the formula for the ellipse, right? There's the equation for the ellipse. Solve it for x. When you solve it for x, you'll get a function of y. Okay. All right. So let's see if we can do that. So this is what x squared is equal to 4 minus 2y squared. Is that right? So what's x there then? Plus or minus, yeah, plus or minus 4 minus 2y squared, okay? So this is the plus side, all right? So this curve is x equal positive 4 minus 2y squared, and this side of this ellipse is x equal minus a square root of 4 minus 2y squared. Okay, but that's all right because I'm going from the left side to the right side, right? So what's this left side? It's going to be the negative value here, right? What's the negative value here? Minus square root of 4 minus 2y squared. Is that right? And then up to positive square root of 4 plus 2y squared. What now? Well, because I solved that equation for x, right? So you just bring the 2y squared over, right? That's x squared, and now take the square root. Did I write minus? Oh, up here. I'm sorry. Right. Now I haven't written the integrand, right? Okay. So I still got to squeeze the integrand in there. So let's leave ourselves some room, because what's the integrand? I think it's all this, right? So 4 minus x squared minus 2y squared. And this is dx dy, right? Okay, so that is our challenge there. We are going to evaluate that. Okay, so you can see that's going to require some work, right? Because we want to evaluate that. So at least the initial part of the integration is not bad, okay? Because I think we can integrate just using the power rule, right? Um, but um, but after we integrate using the power rule, then we're probably going to be introducing some square roots, correct? And that's where things get icky. So we can probably get started here, although it's going to be a little bit messy. But but at least we can get started and then see what happens. Okay. Before we do that, so we're going to go back and try to evaluate this. All right. So we're really going to give ourselves an algebra workout here, but also an integration workout. But I want to point something out to you. Okay. There's another way of writing the volume as an integral. All right. And so look, we used this cross section that was parallel to the XZ plane, right? But as I mentioned last time, you can use horizontal cross sections as well, right? We use vertical cross sections almost exclusively so far in our double integrals, but you can use a horizontal cross section as well. So think of the horizontal cross section that is in the XY plane. In other words, this cross section. What you can do is find the area of that cross section, that horizontal cross section. So find those areas. Of course, you're going to have several of them, right? You're going to have them stacked on each other. So horizontal cross sections, right? And then integrate those together up to, well, the top of the figure here, which is at what? Z equals, is that 4? Yeah, right. It's up there at Z equals 4. So you can also integrate from top to bottom, is my point here. Okay. Now, let me show you how that changes things though. Because what is the area now of this? What is the area now of this cross section? Okay. Well, remember that's an area in the XY plane. So we know how to set up double integrals to find areas in the XY plane. Okay. That's what you were just practicing, or what you're practicing on your homework for tonight. Now, when you find areas in the XY plane using double integrals, what is the integrand? 1, right? So you just use an integrand of 1, and then you would have limits of integration. Well, it would be exactly like the limits of integration we have here. Okay, right? You would use the same limits of integration as we have for our double integral here. Because where did we get these limits of integration, right? They came from this region in the XY plane, right? So look, you can calculate this area, the area here of this ellipse in the XY plane, just in the following way. Set up this double integral. It's minus square root of 2 to square root of 2, and then minus this ugly square root. So 4 minus square root of 4 minus 2y squared up to positive square root of 4 minus 2y squared. But you just use an integrand of what? 1. And then this is still dx dy. Okay. So that gives you this area. And now we want to integrate all the way up where? So we want to compute all of those areas all the way up to all those flat areas, right? All those horizontal cross sections from z equals 0 up to z equals what? 4. So just add on another integral here. But this integral is from z equals 0 to z equals 4. Okay. That seems almost unbelievable. But that, okay, that triple integral also computes the volume. So these two things are same. Seems really incredible, because what appears to be missing from the triple integral, the original formula, but it's not missing. Okay, it really is there. It's incorporated into, it really is there. It's incorporated into the limits of integration. All right, okay. Now, this is not easier to calculate than this. All right, so to actually carry out the integration is going to be just as complicated here as it is here. All right, but conceptually, this might be easier sometimes to set up, right, than the double integral. All right, but we still haven't evaluated the double integral, so now we have to bite the bullet and we have to evaluate that double integral. Okay, so let's do that. And see what happens. What time is it? 12:28. Okay, let's stop for maybe 5 minutes here, okay? Because this is going to be a lot of work, right? So let's take our break here and then come back and evaluate this. Come back and evaluate this double integral. First part, not too bad to integrate, right? You're just going to use the power rule here when you're integrating with respect to x. But when we get to the integrating with respect to y, that's where things start. That's where things start getting fun. All right. So let me pause here and attack this thing. Let me pass out. Pass out. All right. So to start with, this all seems at least partially straightforward, right? So we just have to integrate. That's just an algebraic expression. So we're integrating that with respect to x. So that's not too bad, right? We're going to get 4x, right? And then minus x cubed over 3, right? And then here, just add an x to this term, right? Because that term also is a constant with respect to x. Normally, I'd write the x first, the x factor first, but I'm going to write it second in this case because of what's getting ready to come. Because the limits of integration here, right, are really ugly. So we're going to have to substitute some of these ugly radicals, right, into our integrand there, or into our antiderivative, right? 4x minus x cubed over 3 minus 2y squared x. All right, well, there's just nothing to do there except just bite the bullet and just have to bite the bullet and put that in, right? So see what we get. So the upper limit, right, we're going to get 4 and then square root of 4 minus 2y squared, right? Minus, and then all of this cubed, right? So, ooh, that's really ugly looking. Have a square root cubed over 3, right? And then minus 2, right? Y squared, and then again this square root. And that's just the first upper bound put in, right? Okay, so now we have to put in the lower bound and subtract. So, well, let's see if we can do it there, right? So don't forget this one is negative, right? So I get minus 4 times that square root of 4 minus 2y squared, right? And then um, let's see, when we plug this minus in, that becomes plus, right? So I'll have plus, and then, ooh, we have to be careful about that. We're plugging that in for x. So we're cubing the minus sign, but a minus sign cubed is minus, right? And minus and a minus will be a plus. So this is going to be a plus. So I was right there. So plus, and then again, the square root of 4 minus 2y squared. That's a square there, right? 4 minus 2y squared cubed over 3. Okay. And then plug this minus in here for x. So again, that's a minus and a minus, right? So we get plus again, 2, and then y squared, and then that square root. All right, let's be careful and make sure that we think we did that right. So plug that in here, that negative, so it looks like this, right? Plug that in there. We're cubing the minus sign, so that's still minus. Minus a minus is plus. So we have the 4 minus 2y squared, square root of that cubed over 3. And then plug the minus in here for x. You get plus, right? 2y squared times that square root of 4 minus 2y squared. Well, okay, so, you know, could have better algebraic expressions to look at, right? Okay, or could have simpler algebraic expressions to look at, but that's what we've got. So that's what we have to deal with. So let's try gathering some like terms, right? Because I see this square root term repeated, right? Here and here. So how many of those square roots do we actually have? Here we have 4, right? And then here we have minus and minus. So that's another 4. So that's going to be 8. Okay, so that combines 2 terms. What about these terms? These are both y squared terms, right? Times the square root. So how many of those are there? Do those cancel? Darn it, they don't cancel, right? Here you have a negative 2 of them, and then you're going to have a minus 2 of them again. So that's going to be minus 4 of those, 4y squareds. Square root of 4 minus 2y squared. I move those terms around a little bit because these are very similar, right? They both involve the square root of 4 minus 2y squared, right? So I wanted to put those together because I think they may go together eventually. And then what are we left up? What else are we left with here? Some of these, right? The square root cubed over 3. How many of those do I have? I have minus here and a minus here. So is that minus 2 of those? So minus 2 square root of 4 minus 2y squared. Don't forget that's cubed, right? Over 3. Don't let me make it all hard minus there. I wrote this down ahead of time, so let me check myself. And but don't forget, all of this lives inside that integral, right? So we're still integrating with respect to y. Now, let's see if we can simplify that integrand a little bit. Maybe we can. because you can factor something out to start with, right? A 2. So that's not a lot, but that's something. So we can factor a 2 out of all of these coefficients, right? 2 divides into 8, 2 divides into 4, right? Okay. And of course, 2 divides into itself. So we can factor out a 2. That didn't help a lot. So let's see what that leaves us with here. What, 4 of these, right? And then minus 2. And then factored out the 2, right? So I just get this square root cubed. All that 3. Now, look, I cannot factor anything out of the integrand, right? Except for, so I can't factor anything out here in front of the integrand except for the 2. But these two terms are very similar to each other, right? So these terms, you can group those together. That's what I want to do. I want to group those together inside the integrand. And from those terms, we can factor out quite a lot, can't we? Well, we can at least factor out what? Now, we can at least factor out the radical. And that is useful because that will allow me to combine those terms. Let me show you how. This is minus square root 2, square root 2. So here, actually, I could also factor out the 2, but I'm not, I could also factor out 2, but I'm not going to factor out the 2. I'm just going to factor out a radical. So I have square root of 4 minus 2y squared times, look what's left inside the parentheses here. It's also 4 minus 2y squared, right? And the so look, what I can do is this is just 4 minus 2y squared raised to the power. So I'm going to write that in a weird way. I'm going to write this as the square root squared. Because, you know, when you square a square root, right, just the same as raising power. So I'm going to write these parentheses in a weird way. I'm going to write it as the I'm going to write it as the square root of this squared. And why is that useful? No, it doesn't clear out the radical. But look, here you have this radical, then you have this radical squared. So you've got the same base, right? You've got this radical power, radical squared. So that's the same base. So when you multiply powers that have the same base, yeah, you can add the exponent. So what is this really? Or what's another way of writing that? Yeah. But that's helpful because that's what this is, right? This is the same square root, also raised to the third power. So these are really like terms. These are really like terms just with different coefficients. So how many of these square root do I really have there? Here you have one square root, and you've got 1/3 of that same square root, right? So you combine these two terms, it's what? 2/3 of those, right? So Oh, finally, I'm down to this. 2/3, and then square root of 4 minus 2y squared. And that's cubed, right? Yay. And now I can factor out the 2/3 with the 2. I can factor out the 2/3 with the 2. So that gives me 4/3 in front, finally. And I'm just left now with still a formidable integration to do here, but it doesn't look as bad as before. Okay, whoops, forgot the cube here, right? So now that I'm facing, how do I integrate that? What's the any square root of 4 minus 2y squared? Cannot do that with power rule and substitution. What would you need in order to just use the power rule substitution? What's missing? So you might try just substituting u 4 minus 2y squared, and that so then I would just have square root 2. That's just the same as u. So I would have 3 has power, but unfortunately, I'm going to go using. But when you compute y, then extra factor. So the substitution will. If you had an extra factor of y here outside, so y times its square root, the substitution. This is straightforward. So, okay. All right. So, darn it. So I appear to be having x, but this is where, not really. This is where we have to really dig into our bag of tricks, and we have a trick exactly for this situation. So you may recall, okay, from calculus 2, that sometimes we run into those square roots where substitution is not going to work. We're trying to integrate square root substitution, and so direct substitution doesn't. But sometimes trig substitution. So there are trig substitutions that in certain situations that are helpful. Here is. So you may recall from your calculus 2, you're trying to integrate something of the form a squared minus x squared. So x is the variable, a is just a constant. You're trying to integrate something in that form. It is helpful to make a substitution. X equals a times what constant a times sine. Okay. That trig substitution is often helpful. You know why that trig substitution helps sometimes? Well, what happens is, you're going to see it here, Robert, is if you make that substitution, be able to, using trig identities, you'll end up with square root of, eventually, square root of cosine squared. Then square root of cosine squared is just cosine. So that allows you to eliminate the square root of it. Of course, then you end up having cosine. Maybe that's not as bad. Okay. So let's see if we can use this trig substitution. All right. But now our variable of integration here is y instead of x. Okay. Don't worry about the cube. We're just focused on the square root. So think of the y as being x here in that trig substitution. But in that trig substitution, you didn't have a coefficient on the x. It was just constant squared minus x squared, right? Here we have 2y squared. So I've got to get rid of the 2. Do you know how to get rid of the 2 here? Yeah, you're going to have to do some factoring, okay? So just do a little bit of factoring there. to get rid of the 2. So let's see, what am I going to, so be careful what you're factoring here. I'm going to factor 2 from both of these terms. First, let's leave it under the radical though. So I have 2 times 2 minus y squared, right? But don't forget, all of this is cubed. Now, what can you do with that 2? You can take it out of the radical, right? But of course, 2 is not a perfect square. So when you extract that from the radical, what do you get? Well, you get square root of 2. Okay. All right. You're just going to have to factor that 2 out from under that square root. That's square root of 2. Okay. So you have square root of 2, right? And then times under this square root, 2 minus y squared. Don't forget, however, all of this is cubed, so be careful about that. All of that is cubed. Now, look, I don't care about that square root of 2 anymore, so can't we get rid of that? Can't we factor that out? Let's just put that out of our side here. But remember, this is not just square root of 2, this is square root of 2, but cubed is square root of 2. Well, it's square root of 8 is correct, yeah, but we can write it a little bit simpler than that. Square root of 2 cubed is square root of 2 times square root of 2 times square root of 2, right? What's square root of 2 times square root of 2? 2, and then you have an extra square root of 2 thrown in for good measure, right? Okay, so that's what square root of 2 cubed is. That's what we can factor out in front of the, integrand. So when that goes out, you get what, 8 times the square root of 2 over 3, right? But left underneath here is something we like better to work with. Now we're going to make our trig substitution. But we have to be careful. What's the a value here? It's square root of 2, right? This is, remember, this, you have to think of this as a perfect square. So what you're really squaring there is square root of 2, right? The 2 is the square root of 2 squared, right? So your a value is square root of 2. So what's the substitution we're going to make here? Y is going to be what? And it's sine of something, but what is the coefficient on the sine? It's the a, yeah, which is square root of 2, okay? So the substitution we're going to make is y equals square root of 2 times sine of theta, and I claim all of this will just come out so beautifully, right? If we make that substitution. Now we'll see that in a moment here, but first we have to get rid of the dy. See, we cannot just get rid of the y. Well, we are going to get rid of the y, right? But we have to get rid of the dy as well. So let's compute dy d theta so that we can also get rid of the dy. So what is that? So when you differentiate square root of 2, when you differentiate sine of theta, what do you get? Is that cosine theta? Right? So what is, so solve this for dy. It looks like dy is equal to what? Square root of 2 cosine theta d theta? There we go. So I'm impressed already that we were able to do this. Let's see what we're cubing here now. Okay, so what do we have here? Square root of 2 minus, what's y squared? That's y squared. So if you square this, what do you get? 2 sine squared theta, right? Okay. Don't forget all of this is cubed. And then what was the dy? Well, that's another square root of 2, right? Cosine theta, d theta. So at this point, you're just where you sit. Nice thing. First, I think I can simplify this. First, again, factor 2. So again, factor 2 out of the radical, factor out of the radical, get square root of 2, but don't forget it's right. So square root, right? Okay. But then you also have this square root of 2 from the So what's that going to look like? I was hoping all my square roots of 2 would go away, but didn't quite happen there, right? So see, I'm going to factor a 2 out of the 2 and the 2 sine squared theta. So that's square root of 2 times square root of 1 minus sine squared theta. But don't forget, all of this is cubed, but then you have this square root of 2 also, cosine theta d theta. So can y'all simplify that just by inspection? Square root of 2 times square root of 2, that's square root of 2 to the 4th. That sounds like that should be a number, right? What's square root of 4 power? That 4? Yeah. Square root of 2 to the 4th power is 4. So you can really factor a 4 out in front, putting this other constant in front. So what would that give you? 32? Yeah. But you still have that square root of 2. Here, you just have square root of 1 minus sine squared theta. But don't forget that's cubed. We factored out the square root of 2, so we have this cosine theta also, and then d theta. Now, I'm not going to change my limits. I'm not going to change my variable back to y. I'm not going to do that. Could do that. I'm going to change the variable from theta back to y. I'm going to stick with theta. So that means I need to change these limits in response to theta or y value, right? Okay. So let's see if we can figure out what these correct limits of integration are supposed to be. So let's go back up here, right? Okay. And remember, so we have what? Our lower limit of integration. Well, let's do the upper one first since it's positive. So our upper limit of integration is square root of 2. That's a y value. So let's plug it into this equation where we made the substitution for y. So I have square root of 2 for y equals square root of 2 times sine of theta. Oh, so that means sine of theta is how much? 1. Then what's theta? Isn't that pi over 2, right? Because isn't that's 90 degrees, right? Sine of 90 degrees is 1, correct? Oh, so this upper limit of integration is once we've switched to theta as the variable is pi over 2. If you do the minus square root of 2, you get almost the same thing, right? So you get what? Sine of theta is minus 1. And that's minus pi over 2. Yay. Okay. So this lower limit of integration is just minus pi over 2. Oh, so things are looking up now. Last big thing. Why did I do all of those substitutions? What was the whole point? Get right to this place. Because 1 is 1 minus sine. That is cosine squared theta. That's from the Pythagorean theorem. Remember, cosine squared theta plus sine squared theta is 1. So cosine squared theta is 1 minus sine squared theta. So under this square root, you don't have to have these two terms. You can just write cosine squared theta. And now you can extract the square root. That's the whole purpose of trig substitutions, almost always, is so you can extract the square root and get a square root out of an integral. That's why trig substitution was invented. Okay, so what do we end up with here? Finally, we have 32 square root of 3 over 3, and then this antiderivative. That is going to be cosine to the 4th power. Now, that also is not trivial to integrate, okay? But there's another thing that you may have learned in calculus 2 is how to integrate powers of cosine, okay? That usually also is taught, or at least alluded to in calculus 2. All right, we're not going to go through the steps of integrating cosine to the 4th power. We're going to have Wolfram alpha, okay? But you can, because you can look it up in the table. Also, okay, if you probably don't recall how to carry out the steps with powers of cosine, right? Okay, but there are familiar techniques with powers. So my suggestion, though, is I think you set it up the next year on the campus. So let's first table. What cosine any derivative cosine power table. I think the result turns out to be, if I did this right, let me see. It's not bad. I think it's 3 pi over 8 actually is what that antiderivative works out to be. Okay. Did you have a question, Robert? Oh, I'm sorry. It's supposed to be a 2 there. There's so many 2s and 3s here. I just got them confused. Okay. All right, so we end up with 32 square root of 2 over 3 times, and then this antiderivative turns out to be conveniently, as I mentioned, I think it's 3 pi over 8. So just take that product and simplify that. You end up with, not bad, it's 4 pi times square root of 2. Okay. So finally, I forgot what our question was. Oh, this is the volume, right? Okay. Right. So there's the volume of that quadratic surface there, of that quadratic object, right? Okay. So see, some of these things we can attack, but they're not, these double integrals by hand are not pleasant, okay, to always carry out. Ooh, all right. Let's try this one in Wolfram Alpha since we've just, if I can see if we can type that in. We just have enough time to type that one in before we go to our, before we try doing our next example. So this is not a double integral anymore because we're only doing the last part of this. So we were integrating, wow, what was this? Cosine of something, right? Theta? You can just spell out theta here. To the 4th power, right? From theta equals, what was that? Minus pi over 2? 2 theta equals pi over 2. Whoops. I'm missing there a parentheses, right? Yeah. See if that's 3 pi over 8. Oh, yeah, it is. Cool. All right.
So I see your, so
Yeah, so this is new. I think it will allow you to create this expression. It will create this expression for you. But you can use regular math notation to create the expression. So I guess if you wanted an integral, right, you would put this and then fill these things in, right? Okay. But then it will translate that before it evaluates, it'll translate it to um, um, command line text like this. So you could learn what's the proper syntax in Wolfram Alpha for various things here. Um,
that happens.
right. That's like let's see what this is. We're going to confuse it because we've got multiple things on the same. Yeah. Oh, I see. It thought the limit. Oh, it actually evaluated that. That's neat, right? It thought that integral was part of the limit. Okay. Wow, it's even drawing a picture of that for us. Neat. Okay. Um. So what was your question? Is that
Oh, just that. So actually,
right? So Wolfram Alpha has a syntax, right? A proper syntax. It is a language syntax, though, right? Okay, so it's got words that are commands, right? It's a command line language, and but this program, since people are supposed to be able to use without understanding the correct syntax for Wolfram Alpha, right? They have a natural language interpreter, right? That will try to take your natural language, interpret it, and put it into correct syntax for their program. Okay, but if you use their WYSIWYG input, then it will didn't do it. Last time I did this, it changed that form, showed me what the Wolfram Alpha appropriate syntax was, but it was essentially the same as the natural, very close to the natural language. All right, for that. Okay. All right. Well, we still have one more volume example, so I want to show you what that one looks like. But you guys could certainly set up the. You guys can certainly set up the. Whoa, no, maybe not. Okay, you can have an idea of how to set up the double integral. Okay, here we're trying to find the volume between two surfaces. Okay, so it's kind of like finding the area between two curves. We want to find the volume between two surfaces. So we have this surface, this quadratic surface, 1 minus x squared minus y squared, right? So that's the cone shape here. And then, but this plane, z equals 1 minus y, you can see the plane there, that intersects that surface and cuts off a little piece of that surface, right? This little piece that you see right here. And we want to calculate what's the volume of just that little piece, right? That's between plane and that that cone-shaped surface. So you have an idea of what you're doing, right? Because it's like finding the area of curves. Remember how you find the area between two curves, right? In calculus 1, you find the area between top curve, right? And then the area between the bottom curve, and you take the difference between the two. Same thing. You're going to find volume beneath the cone, right? All the way down to the xy plane. And then we'll find the volume, plane all the way down to the xy plane. And then just take the difference of the two. What's left will be this little problem with what's the appropriate integration, right? And I'm saying all the way down to the xy. I'm talking about beneath this entire plane here, right? Or beneath the entire cone, right? I only want the volume down beneath this little portion. Okay. So what we have to figure out is what is the right region of integration to set up the double integrals for those two volumes so that we can take the difference in those two volumes, right? So in other words, I want to take this little trace, right? Where the surface intersects the um, cone, but so that I'm only computing the right volumes. So what is this curve, this tilted curve, when I project it down to the XY plane? What does it look like on the XY plane, right? So what's the appropriate region of integration? It's obviously going to be some sort of what? On the XY plane, though, David, it's going to be some sort of what? When you take this and some sort of circle, right? Or some sort of ellipse, right? Okay, some sort of oval shape. The question there is just how do we find that? You have a really good idea of how to find that, because how do you find this curve, this trace where these two intersect? What do you have to do? How do you always find where curves intersect, or in this case, where surfaces intersect? What do? You set them equal to each other, right? Yeah, you just set them equal to each other. Okay, so well, we'll look at that next time then. Okay, and that's our last volume example. Then we're going to switch to polar coordinates. Okay, so I'll see you on Monday, right? I won't see you Wednesday, but I'll see you Monday after the break. So remember, the sample test is posted. The test is the 5th, December the 5th. Right. Okay. The week after next. Actually, it's just the week after next. I'm throwing too many next in there.